In this lab analysis video, I'm going to dissect the Malware 3 scenario where we're once again provided with an intrusion detection system alert as though an actual security practitioner might be provided. So if you're a security practitioner responsible for reviewing IDS alerts, this workflow should seem somewhat familiar to you. If not, maybe that's a field you're looking to get into or you're just learning more about security in general. Notice that this workflow does have a clear input with a goal of a clear output in terms of our input is the IDS alert that says something weird is happening on our network, or at least we believe so based upon the signature that's matched. And we want to work through that investigation and basically come up with an output of whether something malicious did indeed happen and what the extent of it is. Now, this is going to be a little different than a real investigation in that we're focused exclusively on a single data source. We're only looking at packet capture data. In a real investigation, you would probably pivot between a few different data sources, probably both network and host-based data. I often get asked which one I would rather have, network or host-based data. My answer is always yes. You need them both for a successful investigation. But for this purpose, we're going to focus just on the packet analysis and what we can determine there, since, after all, this is a packet analysis course. I flipped over now to the Squeal console, and Squeal is an alert console that IDS analysts would use to receive IDS alerts and then start their investigation. So here we just have a single alert in here, and we're running on top of the Security Onion network security monitoring distribution. A little out of the scope for this class, but if you really want a quick way to get going with network security monitoring and intrusion detection, Security Onion is really your best bet. So I've taken a Security Onion installation just out of the box defaults with a default emerging threats Suricata rule set and replayed the first packet capture you were given to generate the alert that I've given you for this prompt. So you can recreate that exercise yourself if you so desire. Now, in this case, we have a single alert and we see the rule that caused the alert to fire here. So this is a signature that matched specific type of activity on the wire. In this case, we're alerting when anything on our home net, so the network we're responsible for protecting, reaches out to an external net, meeting all of the criteria listed here, and there are quite a few of them. In this case, we see that the name of the alert is ET, so that's Emerging Threats, Trojan Crypto Wall Check-in. Crypto Wall, of course, is a very popular ransomware variant, so that's a little bit alarming. We definitely don't want to see ransomware on our networks, but we see that there's been a check-in associated with that malware here. Now, we have a couple different things going on here. First, we have this clause which says flow established to server, and this is flow control. It's a feature of session-aware protocol reassembly in Suricata, and it can tell the direction of a session and whether a session is formally established. We're looking for an established session here and traffic flowing to a server in the sense that it parses the data. Next, we have the URI length. So we're looking at a URI length, HTTP URI length, less than 134 characters. And then we have several of these content matches. So we have a content match here. We have a content match here. We have a content match here. We have several of them. So what that's looking for is a specific series of characters or bytes within the packet capture. And you'll notice they take a specific format. We say content here, and it tells us what content it's looking for, and then it has a few qualifiers after that tell us where that content should lie and some specific information. So this offset and depth qualifiers here tell us where this equal sign should reside within the content of the packet data. It also tells us here that it should reside in the HTTP client body. We have another content here looking for MSIE, and we're told here that it should be in the HTTP user agent. Of course, we've looked at the HTTP user agent, and that should, of course, be a part of the HTTP header. After that, we have additional content. We're looking for accept, followed by the hex characters 3A20. And a few other things of interest here. We're looking for a specific content type, a specific type of URL form encoding, and some hex bytes associated with that. So we're looking for this big long series of content at a very specific depth within the HTTP header. So you see we have a lot of these content matches strung together. We even, it looks like down here in the HTTP header, we have a regular expression being used to do some more complex matching. I'm not going to try to break that down right here, but this is PCRE4 Perl compatible regular expression, which further defines the content match. So this is a very professionally written, very serious, very thorough rule that will precisely detect, ideally, crypto wall check-ins and nothing more and nothing less. So that's what we're looking at, and that's what we want to investigate. Now, in this case, Squill shows us the packet data that matched this specific request. We see in this case it looks like a HTTP post to a specific URL with a specific parameter attached, and there's some form encoding going on there, etc. So that's useful information. We could start here and pivot over, but in this case I'm going to pivot directly over to Wireshark in our other VM so we can begin assessing this capture file and determining again, did something malicious happen? If so, how malicious is it? How bad is it spread? What do we need to do about it? So let's go ahead and look at the packet capture in Wireshark next. I'm now looking at malware3a.pcapng, and this is the capture file that was taken immediately when the alert was received, and it's looking for data captured from the potentially infected host following that initial alert. So it's kind of a forward-looking thing from the time relative of the when the alert was generated. Now in this case, we see we have 162 packets, which isn't a lot to deal with in this case. If I just do a quick scroll through, it looks like most everything we have here is HTTP data. So we're only dealing with one protocol, but I do want to get in a lay of the land in terms of the conversations that we're dealing with. So I'm going to go ahead and open the conversations window. It looks here like we have just a single IPv4 conversation. We have an external host, 184.170.149.44. We have a internal host, 192.168.122.145, and so that is presumably the host that we're responsible for protecting, that is potentially infected and is doing this ransomware check-in as the alert told us, or at least we're led to believe. So this is HTTP traffic. The good thing about that is we can see what's going on in clear text pretty easily. Right here off the bat, we see a connection setup and we see an initial post request. So I'm going to go ahead and just go, let's just go ahead and follow that HTTP stream and look at all that data on the screen at once. It doesn't look like there's a lot of it here, so we can kind of see what's going on. In this case, it looks like we are communicating with the host homealldaylong.com, and we are posting to this specific URL 76n1lm.php with this parameter value here, n equals, and then just a bunch of random text. So that's what's being, it looks like in this case, we're going from, here we go, 192.168 from the victim to the server. So from victim to server here, or I say server, web server in this case. We don't know that it's an actual web server, but at least it's listening to web server type communication. So we see that data is going on. We see that's the header. We see down here, this is in the HTTP body. We have a couple more bits of data being exchanged. And it looks like this is just one single variable, so O equals, and then everything following that is the data associated with that. So I don't know what that is. That's encoded or encrypted, some type of specific string that I'm just not sure what it is right now. But that definitely looks odd. This whole situation looks odd and not necessarily something I would expect to see just based upon these weird bits of data being passed around both in the URL parameter and in the message body. In this case, this server or the remote machine responds. We get a little bit of information about it. It looks like it says it's running Apache with some version information here, powered by PHP. And then we get a response back, which is also another chunk of data that we really don't know what it means. So the question becomes, is this malware C2? And our alert told us it was malware C2, and certainly this is a packet that would match the signature that was provided, and maybe the exact packet that did, as a matter of fact. So chances are this is some type of malware C2 or some type of check-in going on, and that leads us to believe something malicious is installed on the system. But let's go ahead and look at the rest of the packet capture to see if we can find anything else of interest to us. Now, I believe we had 3 TCP conversations going on between these two hosts, and I just clicked into the first one, so that's the one we saw. It looks like they are using the same destination port. It's all HTTP traffic, but we do have a little bit of variance in the characteristics of the connection. So this very first one I looked at is only 16 packets. Looks like 1,600 bytes. The next one is 131 kilobytes, and the one after that is another 1,600 bytes. So the first and third connection look pretty similar, whereas the second one does not. So I think what we're going to do here is let's just go ahead and look at the next one. One of the cool things I can do is let's follow the TCP stream again. This is of the first stream, but there are only 3 streams. So that's the first one we just looked at. I'm going to go down here to the bottom right and just click this plus button and see what we have for the second stream and see if we can figure out anything interesting about it. In this case, the communication looks pretty darn similar. We have another post to what looks to be the same page, but with a different bit of information passed in the URI string. We have a similar format here for the message body being sent over, but different data. And then we have a response from the same server, although in this case our response is much, much larger. We have quite a bit of data. It looks like about 124 kilobytes of data sent over, so that's a lot. And again, we don't necessarily know what this is. And the question you may ask is this encrypted or is it obfuscated? And in a previous example, we looked at JavaScript code being sent over by the browser, and it was just obfuscated. And that's the common technique there, because obfuscation is easy, and you're also passing along the deobfuscation key often to the client because you're executing code within the browser. In this case, code is likely installed on the system itself, so it's not just limited to what a browser can do. It's running with some type of user level or root level privileges on the system, and more doors are open. It could be some type of custom protocol with some custom encryption. Maybe could use a popular open source encryption algorithm. Who knows? But encryption is definitely not out of the question at this point. And the good thing, the interesting thing with these malware samples is unless you reverse engineer them, you often don't exactly know how to decrypt this data without understanding how the application itself is doing it. So here in this second stream, we see that we have a similar format of communication. We just have more data being passed. Let's go look at the third stream. And you know, it kind of looks a lot like the first two, right? Looks like the same page being accessed, but different data being sent in the URI string and in the message body. And here we have a pretty short response from the server, so not a lot of data here in this stream. So they're about the same, and we can go here and let's see, we can apply a filter just to verify in this case. So let's do that, and I will let's just make a filter for all of the HTTP posts. So we'll apply as filter, selected, show me all the posts, and here we go. Here are the 3 posts that we saw, and it looks like, yes, they are all to the same page, this 76n1lm.php, but they're all passing different bits of data. Completely different variables. This one's n equals, g equals, I equals, and different bits of data associated with those. And of course, we all saw that it looks like we got different responses from those as well. So we've kind of reached the end of this packet capture, and we're left with the question, what do we do now? Now, there's not a lot else to reveal in the packets themselves. They're pretty straightforward with just HTTP data being transferred, but we can start to ask questions about the other pieces of information that the alert gave us. One of those was the name of a malware family, right? CryptoWall, which is a very popular type of ransomware used by bad guys. So we can Google that and see what we can find. And I think if you do Google that, one of the first pages you'll come to is this page. It's cryptowalltracker.org. So it's got a wealth of information about CryptoWall, all kinds of different variants of it, as well as things like CryptoLocker and other types of ransomware as well. So we can go here to learn about this malware family and see if we can figure out anything that might confirm what our suspicion is, that this is probably installed and potentially malicious. So let's go ahead and go here to CryptoWall versions here at the top, and let's click on CryptoWall 4, which as of this recording is the current version, and it's what we've identified via our signature, we believe is the version that we're dealing with. Now, there's a lot of interesting things here. It looks like we have an overview, some details on file encryption. That might be, looks like that might be interesting if we have access to the host file system. Maybe we can do something with that. But one thing I see right off the bat that's interesting is network traffic capture. So this is a traffic capture of CryptoWall in action, and that's convenient because that's what we're looking at as well. So let's look at this and see if there are any similarities. Now, it looks like they're using CloudShark, which is pretty cool because it just pulls the capture up right in the browser, so we can look at that. And I tell you, this communication looks pretty similar, right? So just looking at these, it looks like it's already applying a filter for post and get requests for HTTP data. And when I look at this, look, we have a post to a specific PHP page followed by a single letter named variable and a short bit of data transferred in the URI. And it looks like we have some URL form encoded data being transferred here. So this is actually, just looking at it, all these posts, these are really the same sequence of communications that we saw in our capture. So I think it's pretty safe to say at this point that what we see is a sign that there may be crypto wall successfully installed on one of our machines and that they've been victimized and are to some degree the victim of ransomware. Now, we don't know yet if the ransomware was successful, if it actually encrypted their files and asked them to pay a ransom yet. We don't have enough data to back that up. But we do believe it's installed and it's producing these periodic check-ins that are occurring over a bit of time, because it is similar to the traffic we see here. And we know that because we just Googled crypto wall, found crypto wall tracker, and it gave us information about this malware family. Now, unfortunately, not all malware families are as documented as well as crypto wall here is. They're not always going to have packet captures to look at, but oftentimes they will, and you can find examples of these things out on the internet. You may have to look a little bit harder for them, but oftentimes they are there. Now, a great thing about this environment for our scenario is that we're not just limited to the capture we have here, the capture that we took after the alert was generated. We're in an environment that's running a network sensor where they're doing proactive packet capture. And we actually have packet capture that led up to the alert we saw. So things occurring before then. So that's what we want to look at next, is we want to pivot over to another packet capture that shows us maybe how this infection occurred, because if we can figure out how it occurred, we can learn a little bit more about it, maybe develop some more IDS signatures to catch it beforehand the next time, and maybe figure out some clues that would help us remediate it or just better protect our systems altogether. So we don't just want to find out, yes, are we infected? I mean, that's certainly the first priority. But once we find out if we are infected, we do want to find out what the entry vector was so we can prevent it from being exploited again in the future. Switched over now to malware3b.pcapng, which is the second PCAP we're going to look at, and it's the one that was collected up until the point of the alert. So we're looking to figure out what the infection vector was that allowed us to get crypto wall ransomware on one of our victim machines. Now, again, it looks like we don't have a ton of packets here, but we do have more than we did last time. So we have 653. A cursory scroll through sure does look like, again, a lot of HTTP traffic here. Looks like we have some retransmissions here at the end. In this case, I want to go ahead and verify that. So let's go ahead and run a protocol hierarchy and see what we're dealing with. It does look like, yep, it looks like everything we have here is HTTP data or just standard TCP data, or in this case, probably just legitimate HTTP running over TCP. So we know that we're dealing with that, which means we can be a little liberal in how we're examining our data. We can use some filters and really limit this down, which is going to be helpful. I'll go ahead and look at the conversations just to get a picture of what we have going on here. And it looks like we have more than one. It looks like we actually have, oh dang, it looks like we have four TCP, or excuse me, four IPv4 conversations going on between various hosts. It looks like the common thread amongst all those is 192.168.122.145, which is our victim host. So that would make sense, since that was probably what was applied in the filter that pulled this data back, is all data related to this particular victim host for a specific amount of time. So we see you have four different IP addresses being communicated with here. It looks like one of those is maybe familiar, the one we saw earlier when we saw the potential C2 type traffic. So that's interesting. We can look at all these individually and just follow the TCP or HTTP streams, and maybe we'll do that. But first, I want to maybe apply a filter that will let us narrow this down to really the important stuff. So I'm just going to type in here http.request. And I'm doing that because we know this is all HTTP data, and really the magic of HTTP data is all in the request and the responses. So I'm going to go ahead and just get the request here. And actually, as a matter of fact, let's go ahead and get the HTTP responses here as well, so we can have all that, and this can kind of tell the story of the data and the workflow that we want to analyze. We're going to start our analysis here by looking at the first request and response we see, and we'll go ahead and let's just go ahead and down here and expand the HTTP section. We see we have a GET request for the host www.sydneygroup.com.au, and it's for /index.php/services. And for the most part, this looks perfectly legitimate. As a matter of fact, it looks like we have a refer here of a bing.com search. So other than the fact that nobody uses Bing, this looks pretty legitimate. In this case, it looks like they're actually searching for sydneygroup.com.au. So this is maybe a legitimate site that the user was actually intending to go to. So this may be completely irrelevant, or it may be interesting. In this case, we see that the data was returned successfully. We could look into this a little more, but this seems pretty legitimate. So let's go ahead and look at the next thing. And I want to take note to notice the timing here as well. The timing of some of these requests occurring really close together indicates that they were requests generated from an individual page, and it's not a user browsing between things, because the user is clearly not going to browse in less than 1/100th of a second between two pages. So we see the second request here. We see it occurs automatically, which means it was probably a resource that was on the page, that cindygroup.com.au page. If I click on this here, it looks like packet 35. We see that the referrer in this case is indeed cindygroup.com.au/index.php/services. And our GET request is for, looks like this long URI right here, but it's actually on a different host. It's a resource hosted elsewhere. So it's xktzjm.topcentc.top. That's a little weird. I'm not going to say every .top domain I see is evil, but certainly a lot of them are, and that's one that doesn't really look like it means anything meaningful. We see the GET request for /contrary, /some numbers, /quite someone visitor nonsense tonight, sweet await, gigantic dance third, which doesn't make a lot of sense. That seems like gobbledygook, so I don't really know what that is. So this, the last request didn't look entirely malicious, but this one, well, this one looks a little odd. So maybe we want to look into that. So let's go ahead and actually follow the stream on this one on packet 35, just to see if we can see what data was returned. Okay, so in this case, we see our GET request. This is the same information we looked at a minute ago right here. And this is our response. It looks like it's from an Nginx server, and it's gzip encoded data, which of course Wireshark has decompressed for us. Now, we see a response here, and it looks like we have some interesting stuff going on. We see some script data, which is a little unclear. And then we see some, looks like some Flash type content mentioned. So we see object code base, download macromedia flash. That's interesting. We see some reference to some some Flash data here. We see an actual source for that. Okay, so that's interesting. We have a source for what appears to be a Flash file based upon the context that appears in here, and it looks like it's in the directory /occasional/ and then the file name is bxjk, so on and so on. This little file right here. Now, what we see immediately following that is a GET request for that file. So see, we see the path right here, and then we see a GET request for that particular file. The GET request looks pretty straightforward. Of course, the referrer is the site we were just on. And then we see the data returned, and it is identified as the content type, the MIME type application X Shockwave Flash. So we believe here we are successfully downloading this Flash file. The HTTP 200 OK was the response code, and we see a bunch of data that's pretty much indecipherable, and that's because it's binary data. It's this Flash content and not something that's going to be very clearly readable. After that, we do have one more request. We have a GET for /goodness /some numbers and another URL here. Again, on this host, this topcentc.top. And then we have a response back that looks like it's a 200 OK, but no data appears to come back on it. It looks like nothing's here. It says content encoded gzip. There's no actual data report. So in this particular communication sequence between our two hosts, so again, in this case, it looks like it's between our victim, 192.168.122.145, and this other host, 45.32.238.202, it looks like we're downloading a Flash file. And that by itself is not inherently malicious, but it's coming from a domain that looks a little bit suspicious. And whenever you're downloading Flash content, something like that is known to be used with common vulnerabilities and exploitation of them, that certainly makes us a little bit worried here. So that's kind of what we got from this particular conversation. Now we can go ahead and go back to where we were. Let's go ahead and do that. Let's filter on HTTP requests and responses, and we'll see that in that single conversation, we actually went through quite a few of the GET requests and responses here. So we see our GET for this Flash file, and then we see our, looks like our GET for this content that didn't actually return anything back to us. Now we see here we have another request in a similar format as one we previously saw. We saw this one for GET occasional and a bunch of random letters, and then we see one for GET observation and a bunch of letters. So that again looks a little bit malicious. It's to this same 45.32.238.202 It looks like on this same topcentc.top. So it's clearly part of another conversation, as it was not in the HTTP stream we just followed. So let's go ahead and follow this one and see if we can figure out what's going on here. Now in this case, we have the GET request and we have our response back. It doesn't look like it identifies clearly what the data is. It says this is an octet stream, so it's just binary data. We don't know quite what the nature of this binary data is. It does look like there is quite a bit of it here. It looks like 358 kilobytes of it, which is enough for all kinds of interesting things to be going on. And that's really all there is. It's this simple GET request and response and this binary data right here. We don't know what that is. Now, we could extract this. We could carve this out similarly to how we have elsewhere, run that in a sandbox and see what it does. That's certainly one route we can take, but let's go ahead and keep going with the packet capture and see what we can figure out just based on the current line of inquiry here. Now, after the download of this mysterious binary file, we see another request, and this one should look a little bit familiar to you. Instead of a GET request, it's a post, and it's once again to, it looks like a random PHP page with a single letter variable and some random data in the URI. It looks like this case it's to a host called fga-agency.com on 213.186.33.18. Looks like we get a 403 forbidden response to there, and then we see another one of these requests, and it's to 76n1lm.php, which if you remember is the exact same URI we saw in the first packet capture we looked at, and it's to the same host. So this is actually probably the same traffic or the same type of traffic captured a little bit earlier to this 184.170.149.44 host. And I tell you, if we just keep scrolling, it looks like we see more of the same. We see posts to this 213 hosts that are met with 403 forbiddens. We see posts to this 184 hosts that are met with 200 OKs, and it looks like that just keeps occurring before we get to the end of the packet capture file. We know we're looking at everything because everything in here was HTTP data, nothing else really to see. So this one screen and this one filter really tells the whole story of everything that's going on, and we can start to make some educated guesses about what we think happened and how this system got infected. Now, one thing we can note here is notice again the time column, and notice everything here happens pretty darn quick. It looks like we're viewing time display format is second since previous captured packet. Let's do it second since beginning of capture, and things are going pretty quickly. So this is about 86 seconds. So there's enough time in here that some of this could have been human related. But for the most part, it looks like this is pretty darn quick. It looks like the slow areas occur when we see these bigger files downloaded. And then we get down here to these posts, and that's when there seems to be some regular interval of time going on between the like hosts. So here's what I would surmise is going on based upon what I'm seeing in my knowledge of how I know certain attacks to work. In this case, we saw a GET request to a legitimate website sourced from a Bing search. That was probably human-driven, probably perfectly legitimate. Chances are that this sydneygroup.com.au host, or the IP address hosting the content that domain is pointing to, was compromised in some way. And we don't know what that way is. We have no visibility into that. But it was compromised and hosting some potential malicious content. What happened was our browser, or our victim's browser in this case, saw that malicious content when it requested sydneygroup.com.au and was forced to request that itself. It requested that here into this GET request where we saw the flash file referenced, and then it retrieved the flash file. Of course, we see here that the flash file was returned, and my guess would be is that flash file was actually exploiting a vulnerability in Flash. And once it exploited that vulnerability, it could cause the system to download additional content and install it. And that's exactly what we saw here in packet 130. Is we see another request for a binary file. We don't really know what it is right now. We saw that request come down, and it was very shortly thereafter that we started seeing this malware check-in traffic that was identified by our intrusion detection system. So the timeline all fits, that it was a user browsing to a legitimate site, getting infected, unfortunately, because that site had been hacked and redirected to some malicious content. So the workflow I just described is very classic exploit kit activity. Exploit kit operators will infect legitimate websites. You can call that a strategic web compromise, maybe a watering hole attack, depending on what terminology you subscribe to. And then when a legitimate user goes to that site, they get redirected to malicious content. The exploit kit fingerprints their browser to determine what plugins are being used, and redirects them to an appropriate exploit that the toolkit believes might work. In this case, the user was running a vulnerable, probably out-of-date version of Flash. They were redirected to download a Flash file. The Flash file ran, executed, exploited the vulnerability, which allowed the malware code to download an additional binary, which in this case was the CryptoWall ransomware. That's what we saw downloaded. That's what the second file was. And that was installed, and then we saw the malware check-in. So that's all well and good, but that is to some degree still a theory, right? It's more than a hypothesis. Let's say it's a theory and a fairly strong one. If you wanted to validate this a little bit more, the best route to go would honestly be to carve out the file. So we could go here to this envjz2 file. We could follow the HTTP stream of that. And then you could actually carve this file out right here, as we've done with other examples. Kill the clutter out of it, make sure you're carving out all the things you don't need using similar techniques. Take that and then do some malware reverse engineering, either doing that manually, submitting it to a sandbox, and determining if indeed this is a CryptoWall binary. That's a little beyond our scope here. We're not going to do that. This isn't a malware analysis course. But if you do want to do that, I certainly recommend giving it a go. Submitting it to a sandbox. It's not a file that you can't do that with. Just be very careful with it, because this is actual malware. It's CryptoWall malware. And if you attempt to run it, you may CryptoWall yourself. So don't do that. It's the real deal right here. It's not something created in a lab. It's real stuff. So you want to be careful in how you run that. But nonetheless, this is the full description of really not only is the machine infected, it is certainly infected, but how did it get infected? Well, it was through exploit kit activity and the redirection occurring from a legitimate website. Now, this is a very common way that modern systems get exploited. I would say probably the most common right alongside phishing. So this is something you can expect to see in the real world if you're doing security-based analysis, is this exact type of workflow in how users get redirected to malicious content and get bad stuff on their systems.